once you master the content. Okay, here we are, Chemistry 1411. This is chapter 14. We started out with chapter 12. We dealt with kinetics, reaction rates. Then in chapter 13, we dealt with fundamental equilibrium concepts. And the subject of equilibrium is going to remain at the heart of our conversation here in chapter 14, where we deal with acid-base equilibrium. Today, we're going to spend some time talking about Bronsted-Lowry acids and bases. And we're also going to talk about pH and pOH. And we're also going to talk about other definitions of acids and bases besides Bronsted-Lowry. Okay, so let's get started by talking about Bronsted-Lowry acids and bases. Now, acids and bases are a common class of compounds. You know, if you go up to anybody on the street and ask them about acids and bases and say, what do you know? And they'll say, well, I've taken an antacid before, right? I might have used the word there, right? What's an antacid? Well, an antacid is something that you ingest to neutralize a stomach acid. So if you see here, we have acids on the far left. Stomach acid is very acidic, okay? And so the way that you neutralize an acid, and you would have learned this in general chemistry, is by adding a base. So an acid plus a base gives you a salt plus water. So when you take something like Alka-Seltzer or Maalox or Tums, something like that, all you're doing is you're ingesting a base which will neutralize an acid. If you've ever gotten lemon juice in your eye, you know that's, doesn't feel good. And the reason why is because lemon juice is quite acidic. And then you can move your way up here. Seems to be obsessed with fruits and vegetables right here. But anyhow, then we move up to things like milk or water. And we know that water is not acidic, nor is it basic. Okay, if you drink a glass of water, you don't worry about getting burned, because you've heard of people being burned by acids or bases. You don't have to stress about that. Then if you go over to something like soap or ammonia, ammonia is found in household cleaners like Windex, for example. Those are basic. And then if you get all the way up to something like oven cleaner, which is actually quite dangerous, I'm sure many of you have used it before, things like Easy Off or things like that. Those are really strong bases, okay? And so, yeah, acids and bases are found everywhere in all around us, in common household products. What else to say here? Digestion. If you look at the pH of, the stomach, again, you see that it's really low, or I shouldn't be talking about pH because I haven't introduced it yet. But if you look at the acidity of the stomach, you see that it's very acidic. And if you look at something like the large intestine, it's much more basic. Okay, anyhow, something to think about there. And again, as I stated before I started recording this video, that today we're going to look at 3 definitions for acids and bases. The Arrhenius definition, then we're going to tackle the Bronsted-Lowry definition, and then we're going to get into the Lewis definition. All right, so Arrhenius. Here's a picture of Arrhenius, got a nice mustache here. Died a long time ago, almost 100 years ago. And he was the first person to come up with a formal definition for acids and bases. Very simple definition, but easy to understand. That's why we're still talking about it 100 years later. An Arrhenius acid is something, right? It's some kind of substance.
Hello.
Oh, if you have your mic on, if you could mute it, that'd be great. So an Arrhenius acid is a substance, so something that when you put it into an aqueous solution, so when you put it in water, right, it's going to produce hydrogen ions, right? It's going to make H+, okay? Hydrogen ions, we call those protons, right? Because a hydrogen atom consists of 1 proton and 1 electron. So if it loses an electron, all you're left over with is the nucleus, which is just a proton. So that's why we call H+ a proton. So here's a general form. If you take an acid, HA, you put it in water, it's going to dissociate to give you H+, and A-, which is going to be left over. So here you see that we produced a proton. What kind of things can make a proton, or produce a proton? We put them in water. Things like sulfuric acid, hydrochloric acid, hydrofluoric acid. This is acetic acid here, which is the main acid found in vinegar, acetic acid, phosphoric acid, and the ammonium ion. And again, these are examples. This is certainly not an exhaustive example. What's an Arrhenius base? An Arrhenius base is something that when it dissociates in an aqueous solution, it produces hydroxide ions, OH-, right? You think about the strong bases that you would have looked at in general chemistry, things like sodium hydroxide, potassium hydroxide. What about lithium hydroxide? It's not listed here, but that would definitely count as a strong base. Okay, They all have the general form of MOH. What does M represent? M represents a metal, right? Sodium is a metal. Lithium is a metal. Magnesium is a metal. Potassium is a metal. And so how do we know when we have Arrhenius base? If you have a group 1A or 2A metal hydroxide, like these that are shown here, you have an Arrhenius base. So again, we take that ionic compound, we put it in water, it produces hydroxide, and therefore we know that we have an Arrhenius base because we produced hydroxide. Now, you might think, man, this hot diggity darn, this is a great definition, because I remember from general chemistry that sodium hydroxide is a base, and I remember from general chemistry that hydrochloric acid is an acid. Well, that's great, and it is a pretty darn good definition, but the problem is it doesn't include compounds that aren't in an aqueous solution. It doesn't contain acids that don't have a proton to donate, and it doesn't, include bases that don't have hydroxide, right? Remember, I told you that Windex has ammonia in it, NH3, and that's a base. Well, where's the hydroxide in ammonia? I don't see any, right? I don't see any oxygen here. Well, so we have to broaden the definition a little bit, okay, from Arrhenius. And so Bronsted and Lowry came along later on, and they developed what's called the Bronsted-Lowry definition of an acid and base. And again, what it does is it broadens the definition, and they actually simplified it in a way, okay? The Bronsted-Lowry definition is this. If you have an acid, it donates to H+, and a base, instead of producing hydroxide, it accepts H+. Okay, it's just something that accepts a proton. So again, Bronsted-Lowry, acid, donates a proton. Bronsted-Lowry base, accepts a proton. You need to know these definitions, the Arrhenius definition, the Bronsted-Lowry definition. You have to have them, in your noggin. Okay, so if we look at this generic reaction right here, we have an acid and a base. Okay, acid has a proton. The acid is a proton donor. Where's it going to donate the proton to? Well, there aren't many places to give it, right? So it's going to give the proton to the base. Okay, so now you end up with BH+. Why is it BH+? Because you're donating a proton, which is H+. If you're starting with B and you're adding H+ to it, you're going to get BH+, right? You're going to end up with something that's got a charge. And if you have HA, right, and it's losing A-, well, A- plus H+ would give you HA, right? And so you're left over with A-. Okay, so what's left over from the acid? And if you've already read the chapter and you're like, Mr. Dion, I know that these are called conjugate acids and conjugate bases. The answer is yeah, absolutely. But we're going to get into that in a second. Okay, we're going to look at that in a little bit. Now look what it says at the bottom. It says the Bronsted-Lowry definition of an acid still requires that it has a proton. Okay. However, the Bronsted-Lowry definition of bases allows for the inclusion of bases without a hydroxide, right? Like our good old ammonia, right? So Bronsted-Lowry helps us to understand how ammonia is a base. Let me show you how. I'll draw it up here. If you have ammonia, okay, and you put it in water. Now, ammonia is not a strong base, it's a weak base, so I'm going to draw equilibrium arrows. But we said that based off of Bronsted-Lowry theory, that a base is a proton acceptor. Where's it going to accept the proton from? It's going to accept it from the water. So you're not going to have NH3, you're going to have NH4, and it's going to have a positive charge because you're accepting H+. If water loses H+, what are you left over with? You're left over with OH-. Well, looky. I put ammonia in water, and what did I end up making? I end up making hydroxide, right? Ammonia doesn't have hydroxide in it, but it produces hydroxide when you put it in water. So now I want to define a little bit more about this equation right here. The acid plus the base gives you BH+ plus A-. Okay? If you think about this reaction going in the reverse direction, what's happening in the reverse direction? Well, let's examine HA, and again, we're only going in the reverse direction, okay? We're only going from right to left. What's HA doing? HA is losing a proton, right? So HA is in fact a proton donor. That's interesting. I know what a proton donor is. I know that a proton donor is an acid. Well, hold on. Let's take a look at the base that's left over here. If I look at this reaction in reverse, Okay? I see that the base is gaining a proton, right? So this is a proton acceptor. Now, this is what we looked at already, but now if we look at it from the point of view of the products, what was the products back here? Let's look at this reaction. The H plus is doing what? It's donating a proton, isn't it? The A minus is accepting a proton, isn't it? And so we can look at everything, at all four species in this equilibrium process from the point of view of them being acids or bases. So the conclusion is that the products in a Bronsted-Lowry acid-base reaction can act as acids and bases too. Now, the acid and base that are related through the loss of a proton or the gain of a proton, we call those a conjugate pair. Okay? So if you divide this up down here, if you have an acid and it loses a proton, what you're left over with is called a conjugate base. If you have a base and it gains a proton, what you're left over with is called the conjugate acid. So based off of this equation right here, okay, I'm going to back up. Oops, sorry, my computer timed out. Just give me 1 second. Come on. There we go. So if we go back to this equation right here, okay, BH plus right here, okay, what would this be? This would be my conjugate acid, and A minus would be my conjugate base. Why? Because when you look at the reverse reaction, this is donating a proton. And when you look at the reverse reaction, this is accepting a proton. Okay, so conjugate acid-base pairs. All right. So here's another examples, or here's some other examples that are shown here on this slide. Okay, should have divided this a little bit better. But anyhow, the species that's formed when a proton is removed from the acid, we call it the conjugate base. Species formed when a proton is added to a base is called a conjugate acid. Look, if you have water and hydroxide, water, when it behaves as an acid, it donates a proton. So when it loses a proton, what you're left over with is called a conjugate base. If you have ammonia and it gains a proton, right? Ammonia is a base, so what you're left over with is called the conjugate acid. Here's the same analysis, but using the reaction of ammonia and water. Water can behave as an acid or a base. It depends on the situation, but here, since ammonia is a base, it's accepting a proton from the water. So what you're left over with is a conjugate acid. What you're left over with from the water is a conjugate base. If you're still not following me after all that explanation, let me break it down as simple as I possibly can. All you have to know is that an acid donates a proton and a base accepts a proton. If you're having trouble labeling the conjugates, here's what you do. You look at the reaction in reverse only. What's happening to hydroxide? It's taking on a proton. Therefore, if it's a proton acceptor, it must be a base. So it would be a conjugate base. If you take a look at the ammonium ion, what's it doing? It's losing a proton. Therefore, it's behaving as an acid, a proton donor, and therefore it's a conjugate acid. Give me a thumbs up if you follow me on acids and bases and conjugate acids and conjugate bases. Anybody with me on that? Okay. All right. Good. Well, let's take a look at some examples. And I put a lot of examples in here, so I don't know if we'll have time to work through all of them. But let's take a look at A. It says, write the products of the following reactions. And I want to do one more. I want us to label the products as being a conjugate acid, conjugate base, and we're going to label the acids and bases too. So let's start it with A. My screen will stop messing around. So I've got HNO2, that's aqueous, and I'm adding that to water. Now, HNO2 is a weak acid. This is called nitrous acid. Nitric acid, HNO3, is a strong acid, but nitrous acid is a weak acid. So nitrous acid is my acid, which means that water is going to behave as my base. Right? So that means that the nitrous acid is going to donate an H+. So you're going to be left over with the nitrite ion. plus you're going to be left over with a hydronium, right? Why? Because the water is accepting this proton. Okay, now if we analyze this in the backwards or the reverse direction, the nitrite, NO2 minus, is accepting a proton. Okay, so NO2 minus must be my conjugate base, and hydronium must be my conjugate acid. Why? Because in the reverse, it's donating H plus. It's becoming H2O. It's losing a proton. Okay? All right. There we go. Well, let's try the next one. You look at B, you have ammonia. Let's skip that one. Let's do, because we already looked at that one. Let's look at C. Let's go right to C. And it says here for C, you have nitrous acid, okay, plus ammonia. Okay. Now, if nitrous acid is an acid, it's going to donate a proton, and ammonia, we know, is a base. So what are we going to be left over with? We're going to be left over with the nitrite ion, okay, plus the ammonium ion, right? Because the ammonia is a base, it accepts H plus. If we look at the reaction, only in the reverse direction, the nitrite is accepting a proton. Therefore, nitrite is my conjugate base, and the ammonium is donating a proton. Therefore, it is my conjugate acid. All right, there we go. Give me a thumbs up if you follow me on that one. Again, the solution to B is posted to Canvas. I have all the solutions to all the different problems that are in this chapter, so you're not left hanging. What's the answer to this? What's the answer? All the answers, the solutions are in there. I shouldn't say answers, I should say solutions. Very guided answer. All right, let's take a look at some other ones. We could do these really quickly. It says number 2, give the conjugate base for each of the following acids. Well, we know that when we make a conjugate base, we're going to have to remove H plus. What's left over from HCl when I remove H plus? I'm going to be left over with chloride. What's left over from water when it loses H plus? I'm going to be left over with hydroxide. What's left over from hydronium when it loses a proton? Who can tell me what's left over from hydronium? What's the conjugate base of H3O plus? All I'm doing is losing H plus. Thanks, Noah. All right, I'm going to be left over with water. This one here, D, when you see HC2H3O2, this is acetic acid. It is a weak acid. It's going to come up a lot in this chapter, so you have to know it. The Lewis structure of acetic acid is this. You guys remember Lewis structures in General Chemistry 1? Well, here's the Lewis structure of acetic acid, okay? And this proton here is the acidic proton, this one right here. So what am I going to be left over with from acetic acid is I'll be left over with this C2, C2H3O2 with a minus charge, and that is called an acetate ion, okay? Who could tell me what the next one, NH4 plus, what would be the conjugate base of ammonium? Who could tell me what would be the conjugate base of ammonium? NH4 plus. Exactly, NH3. Thanks, Stephen. Ammonia. And then the last one here, it says if ammonia is acting as an acid, okay, if it's in an environment where it can behave as an acid, you'd be left over with NH2 minus. That's called an amide ion. All right, let's move on from there. The next one says give the conjugate acid for the following bases. So all we're going to do is we're going to add H plus to all these. So if I have F minus fluoride, I'm going to have HF. For the next one, I'm going to have hydronium when I add a proton. The next one is CN minus. I'll be left over with HCN after I add a proton. The next two I have carbonate and bicarbonate, right? This is carbonate, okay, CO3 2 minus. I'd be left over with HCO3 minus 1. This is called bicarbonate or hydrogen carbonate, either one. Bicarbonate. And you'd be left over with H2CO3. All right, there we go. Let's move on from there. Are the following conjugate pairs true or false? So are these conjugates hydronium and hydroxide? False. They are, I don't know why I put true. They are false. They are not conjugates. Sulfide and hydrogen sulfide. Yes. Or yeah, these are conjugates. The next one, you have nitric acid and nitrate. Yes, those are conjugates. What about this one here? So this is perchloric acid and chlorate. Would those be conjugates? D. True or false? Yeah, thanks, Mackenzie. The answer is false. They are not conjugates. Next one, I have methanol and methoxide, so CH3OH and CH3O minus. What about E? Could anybody help me out with that? Would those be conjugates? Yeah, thanks, Joey. Absolutely. The next ones are conjugates. These ones are conjugates. And the last ones are not conjugates, right? You'd have to lose 2 protons to go here. Okay, so those would not be conjugates. All right. So now we've got a feeling for what an acid is, what a base is, what a conjugate acid is, and what a conjugate base is. I'm going to have to come back to this slide in a second. But let's move on and talk about the Lewis definition of acids and bases. You'll probably notice if you're an avid reader of our textbook that I'm going in a little different order than the textbook does. Yeah, but I just wanted to teach this before we get too far. I want to talk about the Lewis definition of acids and bases. And what you're going to see is that we will see acid-base reactions where some acids don't contain a proton. Okay. You're going to see some acids that don't contain a proton, and you're going to see some bases that don't accept a proton. Okay, so we're going to see both. So acids and bases that do not transfer a proton. So no donation of a proton, no exception, or no accepting of a proton. We call these Lewis acids and bases. And if you're like, well, if they don't have a proton, how am I going to know if they're an acid or a base, Mr. Dion? Well, let me show you. Okay, the definition is right here. A Lewis base is an electron pair donor, and a Lewis acid is an electron pair acceptor. Okay, you have to know that definition: a Lewis base and a Lewis acid. The way I remember it is like this: the Lewis acid is an acid is an acceptor, and a base is a donor. That's kind of the way that I remember it, like that. Okay, so here we have a reaction between boron trichloride and nitrogen trifluoride. Okay, now what's going on here? Well, the reason that the boron trichloride is behaving as an acid, a Lewis acid, is because it's accepting this pair of electrons, this lone pair, from the nitrogen in nitrogen trifluoride. Okay, and you're making a bond between the boron and the nitrogen. Okay, now before you start thinking like, oh man, this is something completely different. Oh no, it's something way off in left field. Well, the Lewis definition doesn't violate the Bronsted-Lowry definition at all. It only expands it. Okay, if we go back here and we look at one of these examples here, we said, let's just look at this example, this reaction here on the bottom. Okay, we said that a Lewis acid is an electron acceptor. Okay, and we said that a Lewis base is an electron donor. Well, let me show you how. There's a lone pair of electrons on this ammonia molecule. It donates the electrons over here. Okay, so it donates them like that. And then the Lewis acid, my H plus, accepts those electrons. All right. Anyhow, we'll look at more examples of that later on. So don't be like, oh no, I'm not following you 100%. We will look at more examples of that as we progress through the chapter, but I just wanted to show you quickly. I'm going to skip question number 5 right now, which says write the reaction for acetic acid and water, draw the Lewis structure of acetic acid, and show the transfer of electrons. We'll come back to that later. There's other things I want to talk about today, and we'll come back to question number 5 when we have more time. Let's talk about what an amphiprotic species is. If you read the chapter, which I hope you all did before you came to class, you saw this definition of an amphiprotic compound. And an amphiprotic compound is just a compound that can either accept or donate a proton. You think of an amphibian, right? It's a creature that can live in the above water and in water as well. And so amphiprotic means it can behave as a proton donor or a proton acceptor. Okay, so an amphiprotic species can serve as an acid or a base. And a good example would be something like water. Water can act like an acid and water can act like a base depending on the situation. If you put water in a strong acid, well, in that case, it's going to act like a base. Okay, it's going to accept a proton. And if you put water in a strong base, it's going to act like an acid. Okay, it's going to give up a proton to the base. Now, here's another example of an amphiprotic species. Okay, and that's the bicarbonate ion. Another example would be HCO3 minus. Right, the bicarbonate ion can behave as an acid or a base, depending on the situation. So if we analyze these two reactions that I have shown down here, you see that here we're starting with the bicarbonate and here we're ending up with carbonate. So that tells you that the bicarbonate ion here is acting as an acid, right? It's donating H+. The water is behaving as a base in this case, right? Because it's accepting a proton. So here we have our conjugate acid, and here we have our conjugate base, okay? Down here, the bicarbonate is being converted into H2CO3, carbonic acid, and so it's accepting a proton, so it's behaving as a base. Water is donating the proton, so water here is behaving as an acid. Here we have our conjugate acid, and here we have our conjugate base. So these are two great examples because you see how both water can behave as an acid or a base and how the bicarbonate ion can act as an acid or a base, again, depending on the situation. Amphiprotic species. You can see how it'd be really easy for me to write a simple, one multiple choice question on your next exam that asks you about an amphiprotic species. Well, let's talk a little bit more about this whole acid-base properties of water. Right? You think, well, come on, I drink water all the time. I don't feel like it's a strong acid or a strong base. Didn't you say at the beginning of the lecture that it was relatively neutral? And the answer is, yeah, I did say that, okay? So we've seen some examples of acids and bases in water, and we saw how, depending on the case, water can act as an acid or a base. I have a couple of examples here. We talked about what amphoteric means. Sorry, we didn't talk about what amphoteric is. We talked about what amphiprotic is. So amphiprotic is a compound that can donate a proton or accept a proton. Amphoteric just means a compound that can accept an acid or can act as an acid or a base. All right? All right. There we go. Okay. So water is a special amphoteric substance, okay? Or you can call it amphiprotic. Either way, it falls under both, okay, definitions. So water is a special amphoteric or amphiprotic substance, whatever, behaves as an acid or a base, can donate or accept a proton depending on the situation, because it actually reacts with itself to a small extent. We call that the auto-ionization of water. So if you have two water molecules, they can react with each other. So you have two water molecules here, okay, and you produce a little bit of hydronium and a little bit of hydroxide. Now, again, we always draw the equilibrium arrows like this. Let me tell you the truth. The truth is that the arrow would be more like this and then like this, right? You're only producing a little bit of hydronium and hydroxide. How much is it, Mr. Dion? Well, if you write out an equilibrium expression for this reaction, right? Remember equilibrium, we looked at it only a few days ago. The equilibrium expression only includes things that are aqueous or in the gaseous phase. So we're not going to include the water. So we get our equilibrium constant is equal to the concentration of hydronium times the concentration of hydroxide. Instead of just calling it KEQ, we call it KW, okay? So it's the equilibrium expression for water, and the equilibrium constant for the autoionization of water at 25 degrees Celsius is 1.0 times 10 to the negative 14. So you can see that our K, and hey, you spent the whole, bunch of time studying equilibrium. You see that's a pretty small number. So you're like, yeah, I get it. Okay. So maybe when I drink some water, there might be some acid and there might be some base in it, but yeah, it's not a whole lot. In fact, it's only about 2 out of every billion molecules that ionize. So that's why water is essentially neutral. Anyhow, but for any aqueous solution that's at equilibrium, the product of the concentration of hydronium and the concentration of hydroxide has to equal Kw in order to satisfy that equilibrium expression. All right, so this isn't going to change no matter what. This equilibrium expression is always going to be true when we're in an aqueous solution. All right, if you have the concentrations of both the hydroxide and the hydronium being equal, well, in that case, you end up with something that's neutral, okay? And again, I'm sure that many of you have studied pH maybe in high school or biology class. We're going to get into pH soon enough, okay? And that would be a pH of 7, but we'll talk about that in a little bit, okay? So what's going to happen? And this is where you really have to apply your skills that you learned when we studied Le Chatelier's principle in the last chapter. If a substance that changes the concentration of hydroxide or hydronium is added to water, like an acid or a base, you're going to affect the equilibrium, aren't you? Right? And then the autoionization of water is going to be affected. Not the Kw, but the concentration of hydroxide and hydronium, right? Kw is a constant. So let's see what happens here. Two scenarios. What would happen if you added some base, right? If you increase the concentration of base. Now, again, we went over this in the last class. Or the last chapter. It's going to have to shift towards the left. Okay, and since you have an increase in hydroxide, and hydroxide comes from strong bases like sodium hydroxide or potassium hydroxide, the solution would be basic. What would happen if you cranked up the concentration of hydronium, right? If you jacked this up, right? Hydronium is an acid. Therefore, the solution is going to be acidic, and the equilibrium will also shift to the left to try to balance out that change in concentration of hydronium. Again, we're just applying Le Chatelier's principle. Well, with that information in mind, let's try some problems. Question number 6 says bicarbonate is an amphoteric substance. Right? It's amphoteric, meaning it can behave as an acid or a base. It's also amphiprotic, which means it can donate a proton or accept a proton, right, depending on the situation. And it's an important substance because it helps to maintain the acidity of our blood. Write the reaction of the bicarbonate ion with water when it acts as an acid or a base. Well, we saw this already today. It was on a previous slide. I want to go over it with you one more time just to make sure you follow me, and then we're going to speed up a little bit. So if we have our bicarbonate ion, okay, and we want it to react as an acid, it's going to donate a proton to water so that we're going to be left over with the carbonate ion plus hydronium, right? It's behaving as an acid because it's donating a proton. If it were to behave as a base, it's going to accept a proton. So as a base, we start with our bicarbonate. What's a base? It's a proton acceptor. Who is it going to accept it from? From the water. So we're going to be left over with H2CO3 plus OH minus. Okay. Next question says, what's the concentration of hydronium and hydroxide in water at 25 degrees Celsius? We saw this expression a couple of slides ago. Kw, for the autoionization of water at 25 degrees Celsius, concentration of hydroxide times the concentration of hydronium, is equal to 1.0 times 10 to the negative 24. Well, if I start out with water, so I have my 2 molecules of water, Okay, and they're going to be in equilibrium with my hydronium plus my hydroxide. Okay, I'm starting out with pure water. It has no concentration. I have none of this and none of that. But then I have a change. Again, I have no, water doesn't have a concentration. It's a pure liquid. And I'm going to be forming some hydronium and some hydroxide. So at equilibrium, I have the same amount of hydroxide that I do of hydronium. Therefore, we can solve this expression and we can say that the concentration of hydronium, which is equal to the concentration of hydroxide, is going to be equal to x squared, and x squared is going to be equal to 1.0 times 10 to the negative 14. Therefore, x is going to be equal to the square root of 1.0 times 10 to the negative 14, which is the same thing as saying 1.0 times 10 to the negative 14 to the power of a half. You take a half, you multiply it by 14, and you get the x is equal to 1.0 times 10 to the negative 7 molar. So that means that the concentration of hydronium and hydroxide are both 1.0 times 10 to the minus 7 molar in water at 25 degrees Celsius. Give me a thumbs up if you follow me thus far. You're like, I'm with you most of the way, Mr. Dion. Might need to practice, might need to do some more reading. Okay, all right. Well, let's look at something else here. It says, the concentration of hydronium and hydroxide is provided for a particular solution at 25 degrees Celsius. Calculate the solution's corresponding concentrations of hydroxide or hydronium, depending on the situation, and state whether the solutions are neutral, acidic, or basic. Now, I have a solution for this that is posted on Canvas. I'm going to do it a little bit differently here, just a little bit, and this is more for the analysis as to whether it's neutral, acidic, or basic. So watch, and let's see what we're going to do here. So if we have a concentration of hydronium that is equal to 1.0 times 10 to the negative 5 molar. If we go back here, we said that the concentration of hydroxide and hydronium at 25 degrees Celsius in pure water is going to be 1.0 times 10 to the negative 7. So let's write that down. At 25 degrees Celsius in water, concentration of hydronium and the concentration of hydroxide are both equal to 1.0 times 10 to the negative 7 molar. So if my concentration of hydronium is greater than 1.0 times 10 to the minus 7, what do you think this solution is? Is this acidic or basic? And it's not a trick question. This would be on Hate's trick question. Would this solution be acidic or basic, just based off of the concentration of hydronium? It's acidic, exactly. Yeah, because hydronium, H3O plus, is an acid. It's an acid, and hydroxide is a base. So if the concentration of this is greater than the concentration of hydroxide, which we know it is already, okay, we know that this is acidic. And if you're like, I'm not sure that the concentration of hydronium is greater than the concentration of hydroxide, okay, let me prove it to you, because that's what they're asking for. So if Kw is equal to the concentration of hydronium times the concentration of hydroxide, the concentration of hydroxide is simply going to be equal to Kw divided by the concentration of hydronium. 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 5. Right? I'm sure you can do that in your head faster than I can do it, right? It's 1.0 times 10 to the negative 9 molar is equal to my concentration of hydroxide. What's a bigger number? The concentration of the hydronium or the hydroxide? The hydronium. Therefore, it's acidic. There we go. Let's try B, and then we'll move on. No, let's go all the way to C. I keep skipping the B's here. Let's go all the way to C. Again, the solution to B is in the slides that are posted to Canvas. So if I have a concentration of hydronium that is equal to 1.0 times 10 to the 2 molar, would this be an acidic or basic solution? It is not a trick question. based off of Kw. You're going to have to do a little mental math here. Who could tell me? Would this be acidic or basic? Acidic. You could have even answered darned acidic, Mr. Dion, and I would have accepted that too. This is crazy acidic, okay? Super acidic. Let's do the same thing. The concentration of hydroxide is going to be equal to 1.0 times 10 to the minus 14, right? I'll leave the units out. Divided by 1.0 times 10 to the 2. You take negative 14, you subtract 2, and you get 1.0 times 10 to the negative 16 molar is equal to your concentration of hydroxide. That is super duper low. Okay, so this is definitely acidic, and there's our concentration of hydroxide. So you need to have this committed to memory. Okay, you have to know the expression for Kw. Memorize. Okay, and you have to know that Kw is equal to 1.0 times 10 to the negative 14. Okay, you have to memorize that too. All right, there you go. Off the pH chart. Exactly, right? It's crazy acidic. That's something else. All right, well, I'm sure that you've all been exposed to enough science in your lives that you would have been exposed or heard about the pH scale at some point in your life somewhere. In Canada, when I was a kid, they used to have a commercial for a Canadian soap that they were hawking on TV, and they took pH paper and they touched it to the soap because they said, well, soap is basic, and then this soap is neutral, so it's better for you. It's kind of baloney, but whatever. All right, anyhow, so pH and pOH, we're going to start by focusing on pH. pH, if you Google this, and I think I did this a while ago to see what pH stands for, because I asked a colleague of mine, I said, you know what pH stands for? He said, I said, I think it stands for puissance d'hydrogène, which is French for the power of hydrogen. Okay, and it's a measure of the concentration of hydronium in aqueous solution. So really, it's just the negative log of the concentration of hydronium. Nothing more than that. That's all pH is. You need to have this formula memorized. So you need to memorize that pH is equal to the negative log of hydronium. Now, if you understand logarithms and you can do some mental math, you probably realize that if the concentration of hydronium is 1 times 10 to the negative 1, pH is 1. If the concentration of hydronium is 1 times 10 to the negative 2, it's 2, so on and so forth. Remember that H plus is the same thing as hydronium. Okay, those are they mean the exact same thing in chemistry. All right. So if you want to use some mental math when you're solving for logarithms and you're really good at it, by all means, go for it. And if not, no worries, because you're going to have a calculator. All right. Now, you might notice something about significant figures here. I want you to pay close attention to this table. Okay, this table that's over here in whatever this is, beige or whatever. Did you notice that the concentration has 2 sig figs, but the pH has 3 sig figs? Oh, that's kind of interesting. Mr. Dion, you made a mistake. No, I didn't. Okay. Here's how sig figs work with logarithmic functions. However many digits there are, or significant digits there are in your concentration, that's how many decimal places you report in your pH. Okay? Going backwards, however many decimal places there are in your pH, that's how many sig figs there are in your concentration. Simple as that. Okay? Because not only do you have to know how to calculate pH from concentration of H plus or H3O plus, which again is the same thing, you've got to be able to calculate the concentration of H plus or H3O plus, again, same thing, given a pH. How would you do that? You just take the anti-log. If you're rusty on your anti-log, here's the formula, okay? And we even use these a little bit in the first chapter. Remember, we took some anti-logs in the first chapter? Remember that when we were solving for reaction order? I think I might have done it once or twice in class. Most of them, we just solved them in our head, but these ones are tough to solve in your head. So concentration of hydronium is equal to 10 to the power of negative pH. If you really want to get into the nitty-gritty of the pH scale, my slides, it's kind of hard to see here, but you could spend some time taking a look. The pH scale ranges from 0 to 14, okay? So our pH scale, and can you go outside of that scale? The answer is absolutely. But generally, we're going to see it range from 0 to 14, where 0 is going to be strongly acidic, and 14 is going to be strongly basic. And when you have a pH of 7, you can see blood, pure water, milk, around there. That's going to be essentially neutral. So again, high pH, basic, low pH, acidic. When you're around 7, that's neutral. Give me a thumbs up if you follow me thus far. Mr. Neon needs a drink of water. Just give me a sec here. All right. Who's enjoying acids and bases so far? Anybody? Kind of a fun. The first class is always really fun. Just kind of an introduction to the concept of what's an acid and what's a base. Arrhenius, Bronsted-Lowry, Lewis, and then we get into pH. Okay, so we're in section 14.2 now. Okay, well, here you can see how easy it is to come up with multiple choice questions for this kind of material. Okay, find the pH of each of the solutions. There you go, done. I can write a question in 2 minutes. Okay, let's give these a try. Let's try A and C. Let's stick with the pattern that we've been doing today. So we'll start with A. We have the concentration of hydronium. Remember that concentration of hydronium is the same thing as the concentration of H+. And if you're like, why the hell is it that, Mr. Dion? It's because H+ is just a shorthand for hydronium. There's no such thing as just an H+ ion floating around in a solution. It doesn't exist, okay? It's always going to bind to something like water. Okay, so instead of having H+, it's actually bound to water to form a hydronium like that. Okay, so that's why we use, but come on, what takes less time to write? H+, right? So that's why we do that. Anyhow, so if we want to find the pH, our pH is going to be equal to the negative log of the concentration of our H3O+, like that. So that means the pH is equal to minus the log of 1.0 times 10 to the negative 5. pH is equal. I'm going to throw that out there to my students while I punch it in my calculator. And I know that most of you don't have to do that. You probably do it in your head. Does anybody have an answer? A whole complete answer? pH is equal to what? Excuse me. Could you guys type it in the chat, or somebody try typing it in with the correct number of sig figs? That's what I want. Because it is important. Well, who's got an answer here? Ba-ba! Yes, yes, you're all right. Perfect. Thank you. Great. Okay, so the answer is 5.00. Sig figs count, right? Since we have 2 sig figs in our concentration, right? We got them right here. They come from the mantissa. That means we report it to 2 decimal places. Thank you. You're good. You're all correct. Wunderbar, as we say. All right, there we go. Let's try C. Okay, so in C, we have a concentration of hydroxide. Now, there's a couple of ways that you can solve this. We can also have what's called POH. Okay, so pH and POH. I'll show you the answer a couple of different ways. You can either use this formula, POH is equal to minus log of the concentration of hydroxide, and then you use this formula, that pH plus POH is equal to 14.00, okay, or 14 with an infinite number of zeros, okay? That's one way to solve it. I'm going to show you a different way, okay? Why don't we solve for the concentration of hydronium first? Because we know that concentration of hydronium is equal to Kw divided by the concentration of hydroxide, right? We derived that formula a couple of slides ago. So we could say 1.0 times 10 to the negative 14 divided by 3.25 times 10 to the negative 4. Now keep in mind that the Kw, 1.0, it could be 1.000000, whatever, however many zeros you need, okay, times 10 to the negative 14. So I'm going to throw an extra 0 in here. so I can keep my 3 sig figs in my concentration. And when I do that, I end up with what? Let me just type it in here. 1 times 10 to the negative 14 divided by 3.25 times 10 to the negative 4, which gives you 3.08 times 10 to the negative 11 molar. Okay, so now I can plug that into my formula. pH is equal to negative the log of 3.08 times 10 to the negative 11. And I have to double check this one. You guys can do it too. Get your calculators out. Give it the old college try, right? Do it for Clyde. There we go. So you know what? Can you guys type in an answer? We get 10. I'm interested in what my students have for an answer. I'm gonna jot it down here. Anybody get an answer? Yeah. Thanks, Mackenzie. Absolutely. The pH is 10.511. Why? Because we have 3 sig figs in our concentration, so we report the pH to 3 decimal places. All right. Hey, what do you think? Pretty good so far, I think. We're doing pretty well. I'm getting some great answers from my students. Next one asks us to find the concentration of hydronium and the concentration of hydroxide for each of the following solutions. Let's just do, I don't know, let's do A and see where it takes us. Okay. Again, when you come to this class, people, always bring some scratch paper, pencil, calculator, 2 calculators maybe if you need it. Anyhow, and for A, if we're trying to figure out concentration of hydronium, we know that that's equal to 10 to the power of negative pH. So we get that our concentration of hydronium is equal to 10 to the negative 3.2. Like that. All right. So I'm going to throw this out there to my students, and maybe somebody can tell me what the concentration of hydronium is. I'll give you a second. 10 to the power negative. And if somebody has an answer, or you know what, it might be tough to type it because you need scientific notation. Could anybody tell me how many significant figures there will be in the concentration of my hydronium? Who could throw that out to me? Yeah, Mackenzie. The answer is 1, right? Because my pH only has 1 decimal place. Therefore, I'm only going to report my concentration to 1 sig fig. You're like, what? 1 measly sig fig? Yeah, 1 sig fig. Right? When I type it in my calculator, I get 6.30957 blah, 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 times 10 to the minus 4. But the answer that you're going to report is this. 6 times 10 to the negative 4 molar. Done. Okay? So concentration of hydroxide is going to be equal to Kw divided by concentration of hydronium. Where did you get that, Mr. Dion? All I did was solve for OH minus concentration from Kw is equal to concentration of hydroxide times concentration of hydronium, which is equal to 1.0 times 10 to the negative 14. Okay, that's all I used. I'm going to plug in some numbers here. I get 1.0 times 10 to the negative 14 divided by 6 times 10 to the negative 4. And I get that my concentration of hydroxide is equal to 2 times 10 to the negative 11 molar. There you have it, hot dog. We have a wiener. Perfect. Okay, give me a thumbs up if you follow me on that one. You're like, you know what, Mr. Dion, I think I'm with you most of the way. Throw that out there as a problem on the next exam. I'm going to kill it. Hey, you know what? I didn't plan on doing BRC. Can I just throw this out there to my students? I love asking you guys just to probe your knowledge, probe your understanding sometimes. Could anybody answer C without doing any math at all? Could anybody answer C just off the top of their head? No calculator, no pencil, nothing. Jamil says yes. I believe you, Jamil. I believe you. Okay. So if the pH is 7, right? Exactly. Thanks, Ben. Yeah, that's tough to type out, but you did it. Yeah, I see. Yeah, LOL. You're absolutely right. if the pH is 7, right, the solution is neutral, right? Therefore, the concentration of hydronium and the concentration of hydroxide are going to be equal to each other. And we know that at 25 degrees Celsius, we looked at this earlier today, it's going to be the square root of 1 times 10 to the minus 14. And therefore, both of their concentrations are going to be 1.0 times 10 to the negative 7 molar. Okay? Yeah, see, there's one you can just solve in your head. No work required. Okay? So, look, I mean, I'm all for shortcuts, and I'm all for memorizing like mnemonics and things like that. Trust me, Mr. Dion's got a truckload of them, and I like them. However, there is no substitute for really understanding what is going on, right? And I tell you this all the time. I know I repeat myself a lot, but whatever. Think about anything that you enjoy in school, in university. It's always something that you understand. So the more you try to understand what's going on, the more entertaining and more exciting the subject becomes. Okay, this one I probably didn't need a whole page for, but I gave myself a whole page here. Fill in the blanks. If you've got a solution at 25 degrees Celsius, you've got a pH of 0, what would you consider it to be? Who can answer that? Would it be acidic, basic, or neutral? Would it have a pH of 7? Yeah, thanks. Absolutely. It's going to be neutral. What about if you have a pH greater than 7? What if the pH is higher than 7? Yeah, it's basic, right? If it's higher than 7, it's basic. And if it's lower than 7, it's acidic. Okay, here we go. All right, so we have the pH scale. Goes from 0, 7, 14. So this is acidic. This is basic. This is neutral. Neutral. You have to know that pH is equal to minus log concentration of hydronium. You also have to know that the concentration of hydronium is equal to 10 to the negative pH, just taking the antilog. As I told you, POH, which we'll look at in more detail later on, is equal to negative log of the concentration of hydroxide. If you wanted the concentration of hydroxide, it would be equal to 10 to the negative POH. And I told you that pH plus POH equals 14.00000, however many zeros you need. All right. So with those formulas, you can, get the answer to anything here. And let's try some questions that deal with POH very quickly. Again, today we're taking it a little slow. Next class, I'll try to speed up a little bit. But it says here, find the POH of each of the solutions. Let's just do A. I'm going to give my students a second. I'm not going to talk about it. I just want to see if you can solve it yourselves. And then first person who can throw me an answer without looking at the answers for 12. So we're asked to find the POH, not the concentration. Yeah, thanks, Luke. 9.00. Exactly. And that's the solution that I have shown here. If you calculated the pH first, so look, you can solve it the way that I've done here in blue. And let me show you, alternate method would be to calculate the pH first. So you would say pH is equal to minus the log of 1.0 times 10 to the negative 5. So you'd get that pH is equal to 5.00. then if pH plus POH is equal to 14.00, then POH is going to be equal to 14.00 minus pH, and then POH is going to be equal to 14.00 minus 5.00, so POH is going to be equal to 9.00. So either method is fine. You're going to end up with the exact same answer. You're really doing the same thing, right? Okay, and you can give these other ones a shot. Again, I have the solutions posted to Canvas. So if you want to take a look at those, feel free to do that. All right, let's try the next one. Okay, let's try number 13A. I'll give you a second. We spent quite a bit of time working through these, so let me give you a second to think about this one. Here we go. Okay, let's take a look at A. It says to find the concentration of hydroxide and hydronium. We can start by calculating the concentration of hydroxide from our POH. Hydroxide is going to be equal to 10 to the negative POH. We've got our concentration of hydroxide is equal to 10 to the power of negative 12.93. So I take 10 to the power of 12.93 negative, and I get concentration of hydroxide is equal to 1.2 times 10 to the negative 13 molar. And then when I go to work out the concentration of hydronium, it's going to be equal to Kw over the concentration of hydroxide. So that's 1.0 times 10 to the negative 14 divided by 1.2 times 10 to the negative 13. So I get that my concentration of hydronium is equal to 1 times 10 to the negative 14 divided by 1.2 times 10 to the negative 13, which is equal to 8.3 times 10 to the negative 2 molar. Okay, there we go. All right, so we see that when we have a high POH, we have a greater concentration of hydronium than we do hydroxide. Right, so if we have a high POH, we have a low pH, and therefore this solution is actually an acidic solution. All right, let's give the next one B a quick try. Do it as fast as I can here. So for B, we have our concentration of hydroxide is going to be equal to 10 to the negative 4.32. So our concentration of hydroxide, again, should only have 2 sig figs. So we take 10 to the power of 4.32 negative, and we end up with 4.8 times 10 to the negative 5 molar. Then our concentration of hydronium is going to be equal to 1.0 times 10 to the negative 14 divided by 4.8 times 10 to the negative 5. And we get that our concentration of hydronium is equal to 1 times 10 to the negative 14 divided by 4.8 times 10 to the negative 5. And we end up with 2.1 times 10 to the negative 10 molar. So what's the take-home message here? Is that when the POH is less than 7, okay, I end up with something that has more hydroxide than hydronium. So this is a basic solution. All right, now for POH, I'm not sure what you mean by count. You mean the tens place? You mean like this? I'm not 100% sure. Jamil, it's just based on the number of decimal places in the pH. That's all. If you have 2 decimal places in the pH, 2 sig figs in the concentration. That's all there is to it. Okay? Nothing more than that. Number of decimal places in the pH is the number of the number of sig figs in the concentration, or conversely, number of sig figs in the concentration gives you the number of decimal places in the pH. Okay? If you were to try POH, since you know that POH plus pH gives you 14, that would tell you that here the pH is going to be equal to 7.00, and we said that that is neutral. And so the conclusion that we can come to, based off of the math that we just did, is that when you have a POH that's equal to 7, we have something that is neutral. If we have a high POH, right, a great POH, then we're going to have something that's acidic. And if we have a low POH, something less than 7, we end up with something that is basic. Okay, so some interesting formulas. Here's just the derivation for the relationship between pH and POH. I showed you this formula already today. Okay, if you wondered, now where did you get that formula from, Mr. Dion? Well, if we take the logarithm of both sides of our equilibrium expression, okay, then we take the negative log, we get that our negative log of Kw, which is shown right here, is equal to pH plus POH. Okay, what's the negative log of 1.0 times 10 to the negative 14? 14. So you can see how we get this equation right here. Okay, I will never ask you to derive this equation. Okay, I'm not going to write me an essay on where do you get this formula from. No, I just want you to see it. I want you to understand. I want you to know where these things come from. I don't want you to think, oh, Mr. Dion's just pulling these out of thin air. I just have to memorize them blindly. No. That's not right. Okay? I'm going to skip the next slide because it's all information that we've already looked at. And I'm not going to go over this problem with you in class, problem number 16. It's a kind of a long one. But again, the solutions are posted to Canvas. I highly recommend giving this problem the old college try, especially if you weren't following us 100% today. Okay, if you're like, oh boy, I'm not 100% sure about this, give this problem a shot, because I can't guarantee it. Okay, I don't promise anything, but I would think that if you were able to fill out this whole dang thing, that by the end, not only would you be sick of it, you would probably understand what's going on. Okay, with concentration of hydroxide, hydronium, pH, and POH. Okay, so question 16, one to give a try. Now this is something interesting here, and that is the fact that the Kw changes at a different temperature, right? We saw this a lot in this class already. In chapter 13, we said, okay, if we change the temperature, you change the equilibrium constant. So what I want you to do before next class, and I would like you to read the entire chapter and try as many problems as you can, as always, but this is where we're going to start on Friday. We're going to start with this question, number 17. So be sure to give it a try before you come to class. All right, let me just stop right there.